Hello, this is the second part of the lecture on Plabic Graphs. We will now consider Plabic Graphs where we remove the bipartite assumption. So the ones we have seen before are still considered. So the rules of the road is the same. And then here we define a trip to be a walk inside of a path. And we introduce a new definition. So this is a common definition from the literature that I just did not mention in the first lecture. So we say that a Plabic graph is called reduce if every trip is indeed a path as opposed to a closed path. And the definition of trip permutation is the same. So here I have done the trip permutation computation for the Plabic graph G2. So I just check all of the trips from all I in 1 through n. And so I get 3, 4, 5, 1, 2 as my trip permutation in one line notation. And in the previous lecture, we computed the trip permutation for G1, and we have the same trip permutation. And the definition of phase labeling is the same as before. We computed the phase labeling for G1 in the last video. And now the local moves will be slightly different because now we don't need to worry about making sure that the graph is bipartite. So for the square move, I write mi prime instead of instead of m1, I write m1 prime. And again, if the graph has a square with 4 vertices that are all of degree 3, and here I have the requirement because it's possible that we have a Plabic graph with a square but with non-alternating colors. But in order to do the square move, we need to have alternating colors. So if we have all of these requirements, so basically a square that looks like this, then we can apply the square move and basically switch the colors of these 4 vertices. And instead of M2, I write M2 prime. This will be an edge contraction. So if I have 2 adjacent vertices of the same color, I can always contract it into one vertex and basically erasing this edge. And just like before, I can use this M2 prime to allow me to get a square face that would satisfy the condition for applying the square move. So if I have a square face like this, where, for example, this degree is not 3, I can then apply this M2 prime. By adding this extra edge, I get a square face where all of the vertices have degree 3. And the last part stays the same. Basically, if I have a degree 2 vertex, I can just remove that from my Plabic graph. And I cross this out because it doesn't matter if the graph no longer is bipartite. So here is an example. So I start with G1 and I apply M2 prime because currently I cannot apply the square move on this square because of this degree. But after applying M2 prime, I do get this square that satisfies the condition for applying the square move. So let me call this, sorry. So after applying M2 prime, I get this graph, and now this square is in a satisfactory situation where I can apply the square move. So then I go ahead and apply the square move, and I get this new Plabic graph that I'm calling G2 prime. Right, so I've basically replaced the colors of all of these 4 vertices. And for the sake of example, I redraw G2 prime here at the bottom, and now I will apply M2 prime, where I take these 2 adjacent vertices of the same color and remove this edge between them, so I get this just one vertex, and this is my new graph. And I'm calling it G2 because this was the same G2 that I have been drawing. So now let's look at the example of computing the phase labeling for G2 prime. So this was G2 prime, and it's the same rule as before. Here I draw all of the trip permutations, or not the trip permutations, but all of the trips, and I put the label of the starting point on the left side of the path. And I get this phase labeling for G2 prime, and I can do the same thing for the phase labeling of G2. So the 2 graphs are slightly different, but if you compare their phase labeling, you can see that they actually have the same phase labeling, even though in G2 prime you have this face that is a pentagon, and here you have the face that is a square. And again here, this part is a pentagon, but it has the same face label as this square. So some remarks. So the local moves M2 prime and M3 do not change the phase labeling. So for example, the reason G2 prime and G2 have the same phase labeling is because they only differ by a move M2 prime. But the square move does change the phase labeling, and we have seen this in the last homework. But for example, the phase labeling of G1 is different from the phase labeling of G2 prime, and indeed they differ by a square move. So one way to see how they're different is here G2 prime has a phase label 2,4 and G1 does not. And we've said before how if 2 Plabic graphs have the same trip permutation, we can get from one to the other by applying a sequence of the local moves. Here I replace M1 and M2 with M1 and M2 prime. And the trip permutation is also preserved by these local moves. And we've seen some examples of that, how G1, G2 prime, and G2 are 3 different Plabic graphs related by these local moves, and they have the same trip permutation. So these are the 5 Plabic graphs with trip permutation 3, 4, 5, 1, 2 from the last homework. And so we talk about how we can get a map from these 5 Plabic graphs with trip permutation 3, 4, 5, 1, 2 to the 5 triangulations by mapping each face label ij to align segment ij in the pentagon. So this, and I've talked about how this rule where I have, for example, these 2 triangulations where, let's say, the higher one is T2 and T1 is the lower one. So T2 is placed higher because T2 is the result of removing a diagonal of T1 and replacing it with another diagonal of larger slope. And this rule actually works for all n-gon. So I want you to attempt to think of a rule that would work for these 5 Plabic graphs in example 5. And so there should be a rule that you can generalize for larger Plabic graphs, even though I haven't really to tell you how to find them, but start with these 5 in example 5. And you should somehow, so now you know how to match a Plabic graph with the triangulation. So that should help you. And then the rest are some homework exercises. So this is a Plabic graph we've seen before, but we haven't worked with. And I have done part of the computation to find the trip permutation. So we know it's going to look something like 4 and then blank, 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 3. And here you can compute the face labeling of D1, and I have done partial computation, and also I've done some of the face labeling. So the hint is that each face is labeled by exactly 3 numbers, and see how this compares with what you've seen before, like what's special about the label for the external face and the internal face. And here is again an example of how we first apply M2 prime before you can apply a square move. So I start with this D1, and I want to apply the square move on this square, but right now this vertex has 4 degrees instead of 3, so I apply M2 prime by adding this new edge that is in red, and I'm calling it D1 prime. And now from D1 prime I have a square that is in the correct condition to apply the square move. So I apply the square move by changing the colors of the vertices of the square, and I'm calling this D2 prime. So for the homework, compute the face labeling of D2 prime and compare that face labeling with the D1 that you have computed above. What changes and what stays the same? So the next thing is basically looking at what I did here and imitating it, but for another square. And here is a larger Plabic graph. For more practice, you can compute the trip permutation. And I have done 2 of the trips. You can also compute the labeling of this Plabic graph. And again, this is the situation where each phase is labeled by 3 numbers. And I've done some of the partial phase labeling here. And again, you should ask yourself what is special about the label of the external faces and the label of the internal faces. So the external faces basically are faces that are sharing an edge with the boundary, and the internal faces are the other faces that do not touch the boundary. And that's the